All right, so section 8.5 deals with graphing with intercepts. So I'm going to read this excerpt from the textbook. Graphing f of x equals a times quantity x minus p times quantity x minus q. You have already graphed quadratic functions written in several different forms, such as f of x equals ax squared plus bx plus c, which is standard form, and then vertex form, which is g of x equals a times quantity x minus h all squared plus k. Quadratic functions can also be written in intercept form, and this is the form of the title, and that is f of x equals a times quantity x minus p times quantity x minus q, where a does not equal 0, obviously because if a equals 0, this whole thing would equal 0. In this form, the polynomial that defines a function is in factored form, and the x-intercepts of the graph can be easily determined. Remember, the x-intercepts are the point on the graph where they cross the x-axis. Okay, so on this little graph right here, these would be our x-intercepts. So also, if we use the zero product property, we can easily find the values of x for these x-intercepts, which will be super helpful. So I'm just going to do that really quickly. I'll do it below. Actually, I'll do it to the side. So if we have f of x equals a times x minus p times x minus q, what we could do here is set this equal to 0, right? Because this is our y value on a graph, okay? And then equals a times x minus p times x minus q. And what this would allow us to do is use the zero product property. I mean, a is not allowed to be equal to 0, so we can just divide by a, the whole thing, and then 0 divided by a is 0. So now I just get x minus p times x minus q, and I can set both of these equal to 0. X minus p equals 0, and x minus q equals 0. And then if I add p on both sides here, and then add q, I get x equals p, and x equals q. So p and q here are the two values that make y, or f of x in this case, equal 0. So we'll go back over here now. And since they have the same y value, we can easily figure out where the vertex x value is by finding the midpoint between these two x values. So if on this graph right here, if I have p as one of my x-intercepts and I have q as my other x-intercept, they are both going to be the same y value, which means that their x values are going to be equidistant, which means the same distance away from the x value of that vertex. So all I need to do is find the midpoint of that, of these 2 points, and that will give me the x value of the vertex. So to find the midpoint, we just add up the two values and then divide them by 2, right? We're really just taking the average, okay? So to find our axis of symmetry, which is the x value of the vertex, we just take x is equal to p plus q over 2. And then when we find that value, we plug that into our function to find the y value of the vertex. And then as always, this a value that we have is going to be the same a as in vertex form and as in standard form. So if a is positive, the graph will open up like a cup, and if a is negative, it'll open down like a frown. Now the last thing I want to say before we get into our first example is this thing at the bottom. For any factor x minus n of a polynomial, n is a 0 of the function determined by the polynomial. So a 0 is just a value of x that makes the y value of that function equal to 0. So in this case, p and q are both zeros of our function. Because if I plug in p or if I plug in q, the value of the function would equal 0. All right, so for our first example, the instructions say graph f of x equals negative quantity x plus 1 times quantity x minus 5, then describe the domain and range. So what I can do here is figure out my intercepts. We are in intercept form. So I see that in this parentheses, I have x plus 1, and then here I have x minus 5. So I can quickly just set both of these things inside the parentheses equal to 0. So x plus 1 equals 0, and x minus 5 equals 0. The reason I can do that is if I use the zero product property and I plug it into one of these two expressions that are being multiplied, one of these two binomials that are being multiplied, the whole entire function will equal 0, right? Because if this little box equals 0 and I multiply this whole entire thing, that'll equal 0, and then same thing with this. So, and you actually don't need to write out all of these equations because they're pretty easy to do in your head. If I subtract 1 on both sides here, I get x equals negative 1. Well, I could have just figured that out by looking at it. What number plus 1 makes this whole thing equal 0? Well, that's negative 1. And then here it's going to be positive 5. You can do the equations out if you want to, but if you would like to save time, this might be helpful. So anyway, I find that my two intercepts are x equals negative 1 and x equals 5. And these correspond to the points negative 1, comma, 0, and 5, comma, 0. So the next thing I'm going to do on my graph right here is I'm going to plot these 2 points. And it looks like I already have this point plotted, but just for the purpose of this, I'll plot it again. I'm just going to make my marker a little bit thicker. So anyway, we have the point negative 1, comma, 0, so that's right here. And then I have the point 5, comma, 0, so that's right here. Okay? So I have these 2 points. Now, if you remember, in order to find the vertex, which for any parabola that we're graphing, we need at least 3 points. In order to make your graph look better, I would suggest using at least 5. But in order to have a unique parabola, we need at least 3 points. And the way that we're going to do that is we just find the midpoint. Because these values are the same y value, I just have to find the value in between them. Now, since we've already graphed this, it's actually pretty easy. I can see that 2 is right in between. 2 is 3 spaces away from this point and 3 spaces away from this point. Now, if I didn't graph them yet, what I could have done is just taken my two x values, x equals negative 1 plus 5, and then divided them by 2. And that would help us find the midpoint there. So this is x equals, well, negative 1 plus 5 is 4. 4 divided by 2 is 2. So that is our x value. Okay, but in order to find the point for the vertex, we need the x and the y component. So that is going to be, what I'm going to have to do is plug this x in back into our original function up here. Okay, so our function is f of x equals negative parentheses x plus 1 times x minus 5. So what I want to do here is find f of 2, because we know 2 is our x component of the vertex. So this is f of 2 equals negative 2 plus 1 times the quantity 2 minus 5. And then when I simplify this, well, this is negative 3 times negative 3. And that is going to give us the point positive 9. So f of 2 equals positive 9. So our vertex ordered pair is going to be 2, because that's our x value right here. And then comma 9. So if I go back to the graph, I want to plot the point 2, comma 9. So my x value is 2. And then my y value is going to be 9. So I'm going to plot this point right here. Something like that. Okay, now I have my 3 points. Okay, what I would personally do is I would make a table and I would plug in, because now I've figured out my vertex, I would plug in the x value for maybe 0 and 1, and then from that we could figure out the x value from 3 and 4. But technically you don't need to do that. So what I'm going to do now is just sketch a parabola from our vertex to our 2 intercepts. And I'm literally sketching it, because if I try to do just one perfect line through, it would look terrible. And then we do our arrows at the end because this parabola goes on for infinity. All right, so this is our sketch of the parabola that represents the function f of x equals negative quantity x plus 1 times quantity x minus 5. Now we need to describe the domain and the range. Okay, so I'm going to do that in this little box right here that I've just drawn. And the domain, well, there's no numbers that I'm not allowed to plug in. Like I'm not taking the square root of anything. I'm not dividing by anything. So x can be anything. So x equals all real numbers. Now y, or f of x, for the range, the largest point for f of x, we solve for that. The vertex, the maximum point of this, is going to be 9. So all the possible f of x values are going to be 9 or lower. So f of x is going to be less than or equal to 9. So this is my domain right here, and this is my range. All right, so for this next example, I'm not going to go as in depth as I did last time. I'm just going to kind of do this one a little bit faster. So we have f of x equals 2x squared minus 8. All right, so since we're in this section we're graphing using intercept form, what I'm going to do is I'm going to factor this out and make sure that it is in a form that I can use for intercept form, and then I'm going to graph it. So I notice right away I have two even numbers, so I have 2x squared minus 8. So I can factor out a 2 right away. So I'll rewrite this as 2 times the quantity x squared minus 4. And as I factor out that 2, what I notice is I have a difference of squares here. So x squared minus 4. Okay, so x squared is a perfect square, and then 4 is a perfect square. So I can rewrite this, factored out, as f of x equals 2 times x plus 2 times x minus 2. So this is great because now we are in intercept form. I have my two intercepts here. Okay, so I know that my intercepts are going to be negative 2, because negative 2 would make this 0, and then positive 2, because positive 2 would make this 0. Okay, so my intercepts are negative 2 and 2. So I'm going to plot those on my graph right now. They are right here and right here. Close enough. All right, so now the last thing I need to do is I need to find the value of the vertex here. And this is lucky for us because I can just tell right away that the x value of the vertex is going to be 0, which makes our lives super easy because if I plug in 0 right here to this function, 0 squared is 0, 0 times 2 is 0, 0 minus 8 is negative 8. So I know that my vertex is going to be the point 0, 8. We also could tell that our vertex was going to be 0 because this function is technically in standard form right now, and there's no b value. If there's no b value, then the x value of our vertex will be 0. Okay, so anyway, I'm going to plot that now. So I'm going to plot that at the point 0, negative 8, which is right here. All right, so now the last thing I need to do is just draw my sketch. I'm going to do the same thing. I'm not going to try one clean parabola because that's going to look really messy if I do it that way. I'm going to try my little sketch here. This is how I'd do it if I was doing this on a pencil and paper. Something like this, okay? And these arrows aren't pointing straight up. They're pointing a little bit to the right as well, and here a little bit to the left. And this is a general sketch of our, it's a rough sketch, I should say, of our parabola for the function f of x equals 2x squared minus 8. Now the last step we need to do is describe the domain and range. So just like any parabola that we have, the domain is going to be x equals all real numbers, because we can plug in any number for x. There's no restrictions that I can plug in for x. And then for the range is going to be, let's see, this is f of x. So the range is going to be f of x. Well, the smallest value here is -8. Every other y value is larger than -8. So the range is going to be f of x is greater than or equal to -8. So this is our domain, and this is our range. All right, so for this next example, it says find the zeros of f of x equals x minus 1, that quantity, times the quantity x plus 2. So this one's actually pretty simple. A zero of a function is just find the x value when that makes the entire function equal 0. So all I have to do is set this f of x equal to 0 and then solve this equation. And once I plug in 0 for this, it actually becomes a zero product property problem, and that's something that we've been doing for a while now. So this is 0 equals x minus 1 times x plus 2. And you can set both of these equal to 0, or you can just do them in your head. What numbers are going to make these two expressions equal to 0? And then, then if I multiply 0 times anything, I'll get 0. So anyway, you can add 1 here, and then subtract 2 here, and I get my 2x value. So x is 1, and x is -2. So my zeros are x equals 1 and x equals 2. Sorry, this needs to be -2. So x equals 1 and x equals -2 are my zeros for this function. The next example is similar to the previous example, but this time we just need to factor out our things. We're going to set both functions equal to 0, and then we're going to find our x values. So the only new concept here is naming those x values zeros, okay? And relating those zeros to the intercepts. The y value is the 0, and then the point of the 0 is the x-intercept. So anyway, what I'm going to do first is set this function equal to 0, -2x squared minus 10x minus 12. And then what I'm going to do is I'm going to factor out a -2. Okay, it's always good to be able to factor out a negative number. So I get x squared plus 5x plus 6. Okay, so now when I factor this, this is a quadratic expression. I can factor this pretty easily. Okay, I need to find two numbers that add up to 5 and multiply to 6. I can tell right away that the only ways that we can multiply to 6 are by doing 1 times 6 or 2 times 3. 1 plus 6 is 7, so that's not going to work, but 2 plus 3 is 5. So I can rewrite this as 0 equals -2 times x plus 2 times x plus 3. And what this will do is if we FOILed this out or multiplied this out, we would get this expression. And now I'm in intercept form, technically. So I can just set all of these equal to 0. I can always, anytime there's just a coefficient out here, I can divide it out because 0 divided by any non-zero number is 0. So I can divide this out by by -2 on both sides. So I get 0 equals x plus 2 and x plus 3. And now you could set both of these equal to 0, or you could just say, okay, what number for x for both of these is going to make this equation equal to 0? So you can tell that for positive 2 here, we just have to do the opposite, which is -2. Same thing here for positive 3, we have -3. So my x values are x equals -3 and -2. So these are my two zeros of the first function. Now the next example over here is h of x equals x minus 1 quantity, and then times the quantity x squared minus 16. Well, we're going to set this function also equal to 0, because that's what we're trying to do. We're trying to find the zeros here. So 0 equals x minus 1, but I see another difference of squares. So I'm going to save myself a step and just write this out as x plus 4 times x minus 4. Well, the quantities, obviously. So now, all I need to do is set all three of these equal to 0. But once again, if you want, you can just do the shortcut, which is just say, okay, what number is going to make this thing in parentheses 0? What number is going to make this thing in parentheses 0? And same with this one. So here, what minus 1 is 0. That's positive 1. So I know that 1 is going to be a value, a 0. And then here I have what number is going to add positive 4 to get to 0. That's going to be negative 4. And then over here, what number can I subtract 4 to get 0? And that's 4, positive 4. So these are my 3 zeros of this function. This is a cubic function. We'll go over actually a graph of a cubic function in intercept form in a later example for this lesson. So the next example says, use zeros to graph h of x equals x squared minus 2x minus 3. So what that basically means is it wants us to factor this out and then graph using the zeros that we factor out, using the methods that we just went over in previous examples. So the first thing I want to do is factor this. And I see that I have negative 2 for my b value and negative 3 for my c value. So I need to find two numbers that are going to multiply to negative 3 and then add to negative 2. And I can think right now that since this b is negative, the negative number is going to be bigger. So the only way to multiply to negative 3 is either negative 1 times positive 3 or positive 1 times negative 3. And positive 1 plus negative 3, does equal negative 2. So I'm going to break this down into x and x, and we have a negative 3 and a positive 1 here. Okay, and then this is our h of x function, of course. So my first thing I'm going to do is I'm going to graph the intercepts, okay, the x-intercepts. So this value, to make this whole thing in parentheses 0, this x value has to be positive 3. So it's going to be x equals 3. And then here, this is going to be x equals negative 1. And if you don't believe me, just plug these back in and see what your value of your function equals. Okay, so now I'm going to plot these points. These points are going to be 3, 0, and negative 1, 0. So I'll plot them. It's going to be right here and right here. So those are my 2 points, and I'm sorry for them being hilariously large. That just helps me sketch the graph. And now the last step is I need to find the vertex. Well, there's a couple of things we can do to find the vertex. We could either say I know the x value is going to be halfway in between here, or we could use our old x equals negative b over 2a from standard form. Because I've already plotted these points on the graph, and I can tell that this point is right in between them, I'm just going to do that. So this is the point x equals 1. So I just need to find the corresponding h of x value, and I can just do that by plugging in here. So my x value is going to be 1, like I just said. So x equals 1. So h of 1 is going to equal, and I'm just going to plug into the factored form because I think that will be easier, but you could plug into either forms. It's going to give you the same value. So h of 1 equals 1 minus 3 times 1 plus 1. So this is going to be negative 2 times positive 2, which equals negative 4. So when my x value is 1, h of 1 equals negative 4, which is the point 1, 4. So that's going to be, 1, negative 4, I should say, which is going to be right here. So I'm going to plot my last point. And the last step is to just draw a sketch through this graph. My suggestion, once again, would be if you want to make your graph as accurate as possible, graph as many points as you can that will fit into your grid. But here, just to show you how we can use the intercepts, I'm just going to use these 3 points. And once again, I'm just sketching. I'm always including my arrows because this is going on forever. All right, so here is the sketch of the graph that I made. And that's how to do this one. All right, so for the 6th example, we're told to write a quadratic function in standard form whose graph satisfies the given conditions. So the first example, or the first part of example number 6, we just need a function, quadratic function that has a vertex of negative 3, 4. So what I'm going to do is I'm just going to use vertex form because that would be the easiest form given the vertex. So vertex form, if you remember, is y, and you could have used f of x instead of y, but I'm just going to use y here. Y equals a times quantity x minus h squared plus k. This is vertex form. So all we need is a vertex of negative 3, 4. it doesn't specify what our a value has to be. So my suggestion is if it doesn't specify, pick the easiest one, which is going to be 1. But you could pick any a value besides 0. So I'm going to have a equal 1 here. So I'm going to plug in 1 here, which means I don't need to plug in anything. And I'm just going to plug in my vertex. So remember, in vertex form, h is the x value of the vertex, and k is the y value. So since I'm plugging in negative here, it's going to be a double negative, which is going to change to a positive, but we'll see that as we plug it in. So y equals, I'm plugging in 1 for a, so I really don't need to plug in anything. And once again, you could have plugged in whatever you want for a besides 0, times x minus negative 3 squared plus 4. Okay? So now all I have to do is kind of make this look a little nicer. Minus a negative is a positive, so that's y equals the quantity x plus 3 squared plus 4. All right? The last thing I have to do is I have to write this function in standard form. Okay? And the reason is because the instruction said that. So I know that since I'm squaring this binomial, I know that the pattern is a squared plus 2ab plus b squared. So for this specific case, it's going to be y equals x squared plus 2 times x times 3, which is going to be 6x, and then plus 9. And then I have to remember this plus 4 right here. And then I just have to add 9 and 4, and then I will be in standard form. Y equals x squared plus 6x plus 13. And this is the answer. This is one of the many answers for part A. Because we had no specification of what our a value needed to be, this is one of the many answers. This is probably the easiest answer. So this is the answer for part A. All right, let's scroll back up to find part B. For part B, we need to write a quadratic function in standard form whose graph satisfies the conditions that it passes through -9, 0, and it passes through -2, 0. All right, so this is actually super helpful because these are two of the x-intercepts. Remember, the x-intercept is the value of x when y equals 0. Y equals 0 here, y equals 0 here. And because I have -9 here and -2, I can just make it x plus that equals 0, or x plus the opposite of that equals 0, and x plus the opposite of this equals 0 as two of my factors. And then this point will help me find my vertex. So I have, for part B, I have -9, 0, and then -2, 0. We'll start with that. So because these are both x-intercepts, -2 and -9 are zeros. So one way to kind of see this is if I set x equal to -9, all I have to do is add 9 on both sides, and now I have x plus 9 equals 0. So this is one of my factors, if you will. And then over here, I'll do the same thing. X equals -2, I add 2, and I get x plus 2 equals 0. Okay, so now I have two things that if I multiply together, they both satisfy this criteria that these values will cause it equal to 0. So in my function, I'll call it, we'll call this g of x. G of x equals, well, I don't know what a is yet, but I can figure that out soon. And then I'm just going to multiply this times this, because that will guarantee me that these 2 points are on this parabola. So a times quantity x plus 9 times x plus 2, because once again, I know this is a bit confusing, but if I plug in -9 here, this whole thing will equal 0, and then this will be the y value will be 0. And then over here, same thing, -2, if I plug this in, this will be 0, and then that'll make this entire function 0. Now, the last thing that I need to be sure of is that the point -4, 20 is a part of this function. And this will help us find our a value right here. So I need the point -4, 20. So whenever I'm missing a parameter right here, all I got to do is plug in -4 for all the x's, and then 20 for y, or in this case, for this whole entire g of x, to find a. So I'll plug in 20 for g of x right here because that's our y value. And then a times quantity, -4 is our x value. So I'll go -4 plus 9 times -4 plus 2. So now I'm going to simplify this. -4 plus 9 is just +5. So this is a times 5. And then -4 plus 2 is -2. So now I get 20 equals a times 5 times -2. I'm going to scroll down here. And -2 times 5 is -10. So I get -10. A is equal to 20. Then I can divide by -10 on both sides to get that a is equal to -2. So this is our a value. And then what I'm going to do is plug this a value in here to our function. So now I'm going to rewrite our function right here as g of x is equal to -2, because that's our new a value, times x plus 9 times x plus 2. And then the directions say to write it in standard form right here, standard form. So we just need to multiply this all out and write it in standard form. So what I'm going to do first is distribute this -2 to the x plus 9. So I'm going to get g of x equals -2x minus 18, and then in parentheses, that's in parentheses too, x plus 2. And then I'm going to FOIL this out. So -2x times x, well, that's -2x squared. And then I have -2x times +2, which is -4x. And then I have -18 times x, which is -18x. And then I have -18 times 2, which is -36. So I get g of x for my final answer after I combine like terms here. G of x equals -2x squared minus 22x minus 36. And this is our final answer here. All right, in these last two examples, we're actually going to talk about cubic functions, which are a polynomial function that the highest degree term is x to the third power. So in quadratic functions, which we've been doing, we've had x squared as our leading degree. But here, for our cubic functions, we're going to have x to the third power. And what we're going to do, the way we're going to do this is by using intercept form. You'll learn a lot more about this in Algebra 2. But for now, we're going to use what we know in order to do this. So the first thing I want to do is I want to factor out what I can. So I can factor out an x out of both of these terms, which is going to be super helpful. So this is going to be f of x equals x times x squared minus 4. And then once again, I see a difference of perfect squares. So I can factor this again to have I'll rewrite it over here. F of x equals x times x plus 2 times x minus 2. All right, so now the hint is to use zeros. So I can easily find my zeros now. I just have to set this equal to 0, the f of x equal to 0, and then I get x, and then x plus 2, and then x minus 2. And I can easily tell my zeros. Well, x right here, all I would do is set this equal to 0. So I know that x equals 0 is one of my zeros, probably the easiest one to find. And then over here, I have to figure out what number could I plug in for x that would make this whole set of parentheses equal 0. That's going to be -2, because -2 plus 2 is 0. So x equals -2 is another 0. And then x minus 2, what number will make x minus 2? Well, that's going to be +2, because 2 minus 2 is 0. So now I know that all three of these points are going to be on this x axis right here. So I'm going to plot these right now. This is going to be the point 0, 0, the origin, and then -2, 0, and then 2, 0. So I'm going to plot those right now. So they're going to be here, here, and here. So now that we've plotted the intercepts right here, the x-intercepts, the not so exact way that we're going to do now is just plug in the x value for points in between here. When you take calculus, you'll figure out how to find the exact local maximum and local minimum here. But for now, we can just pick the 2 points in between our intercepts, which is -1 and 1 for x. So if I have x equals 1 right here, because that's in between these two, 0 and 2 right here, and I plug it in here for this function, x times x plus 2 times x minus 1. Actually, you know what? It's probably going to be easier to plug it into f of x equals x cubed minus 4x. So f of 1 is going to equal 1 cubed minus 4 times 1, which is the same thing as 1 minus 4, which is 3. -3, excuse me. So the ordered pair is going to be 1 comma -3. So I'm going to plot that right now. Now I'm going to do the same thing for x equals -1. I'll do f of -1 equals -1 cubed and then minus 4 times -1, which is going to be -1 and then plus 4, which equals +3. So my ordered pair is going to be -1 comma +3. And then what I do is I'm just going to plot that point, and now I can sketch a graph through it. So you obviously don't know a whole lot about cubic functions yet, but it's basically just going to start from down here. It's going to go up here until we stop here, change direction, go in here, and then change direction again, and then that'll be our graph. So I'm going to sketch that really quickly. So I'll include my arrows here, and then I'll turn it around like this. Then we'll curve it back up, something like that. And it will look something, undo that a bit because it's going to curve up a bit more. So something like that. And I'll include my arrow here. So something like that. So obviously it's impossible to draw a perfect curve freehand, but that's the general idea of graphing this function. All right, so for our last example, we have a cubic function, and we can kind of see what it looks like right here. And we have all three intercept values, which is going to be helpful. And then we have some point, which is going to help us find our a value. The instructions say the graph represents a cubic function. Let's write what that cubic function is. So we're going to use all of these points, all of these x-intercepts, to help us out at first, and then we're going to use this to find a. So I see that I have the point 0, 0. So one of my x values is x equals 0. And then I also see that I have x equals 2, which once again, if I subtract 2 on both sides, I get that x minus 2 is equal to 0. And then the last one I have is x equals 5 here. So then if I subtract 5, I get x minus 5 equals 0. So now all I have to do is just multiply x times x minus 2 times x minus 5 for our function. But I need to make sure that this 3 comma 12 fits in here. So I don't know the leading coefficient, so I need to figure out what my a value is. So my function, I'll do f of x equals some number a that we don't know yet, times x minus 2 times x minus 5. All right, I'm going to move that over a bit, zoom in. All right, and now, well, I'll move over for a sec. We need to include this 3 comma 2 to find our missing parameter a. So I need to plug in 3 for my x value, and then 12 for my entire f of x value. So I'll just write that point over here, 3 comma 12. So I'm going to plug in 3 for all of the x's, and then 12 for f of x, or the y value, essentially. So it's going to be 12 equals a times 3 times 3 minus 2 times 3 minus 5. And this simplifies to 12 equals a times 3. 3 minus 2 is 1. And then 3 minus 5 is negative 2. So I get 3 times 1 is 3, and then times negative 2 is negative 6. So I get 12 equals negative 6a. And then I divide by negative 6 on both sides. And I get negative 2 is equal to a. So all I need to do is plug this a value into my original equation up here. So if I write it over here, I get f of x equals negative 2 times x minus 2 times x minus 5. And it does not specify to put it in standard form, so this is fine. This is our final answer.